In this video, we're going to be looking at an example on calculating utility costs. And what we've been looking at the total manufacturing cost that involves raw materials, waste treatment, utilities, operating labor, and the fixed capital investment, as well as depreciation, which we're going to be delaying our discussion of that until the next chapter. And so we need to come up with estimates for all of these terms in the equation for the cost of manufacturing. And right now we're focusing on the cost of utilities. So we have, from our last lesson, this table that is a reasonable estimate of utility costs. And at least it's a place to get started until you actually know something. And so let's look at an example from the textbook. So they want you to estimate the utility cost producing circulating cooling water using a mechanical draft cooling tower. So these are the things that you've seen on tops of buildings, you know, when they have for their air conditioning systems, etc. And in this particular case, we're going to use a basis of 1 gigajoule per hour of energy removal from the process unit. And we want to figure out what the flow of cooling water is, as well as the utility cost. So, let's get started. To figure out the flow of water, we need to start with an energy balance. We know that the amount of energy is 1 gigajoule per hour, and we know that M dot C sub P delta T will give me a good estimate if I have just pure temperature change. Okay, so if I had a 10-degree temperature change on my cooling water, which is a typical value, okay, and C sub P of roughly 4,180, then this would give me the mass flow rate of water to change that 10 degrees. Okay, now this is going to be done by evaporation. So therefore, what I need to do is look at the heat load for the latent heat of vaporization. So if you look that up, 2417 kilojoules per kilogram is the value for 35 degrees C. And so the heat of vaporization divided into the heat load tells me what the water evaporation rate is from the tower. So how this energy change is going to be accomplished by vaporizing water. Okay, so this tells me that I've got 413.7 kilograms per hour of water being vaporized to cool 23,923 kilograms of water. Alright, so if you look at this, that means it's nearly 2% of the circulating water is going to be evaporated. Now, that's important for a couple of different reasons. One is it tells me what my water needs are, but in particular it tells me where the water is going. So I'm going to be losing some of it in a fairly significant amount. Now we're also going to lose some due to wind. So if I've got wind flow, the estimates are that it's going to be up to 0.3%. And if I've got that 0.3% wind loss, then I need to add that in also. Now, this is something that is perhaps new to you. So, unfortunately, water always contains various kinds of salts, okay, various inorganic compounds in there. And there's a maximum that you can have. So you need to know what that maximum allowable amount is. Now in this case they've defined it as S, okay? So S is the mass fraction of salts, essentially, that are in the system. So it's the concentration of salts in the cooling water loop divided by how much is in the makeup water. Okay? Now, typical values, yeah, between 3 and 7 they say, okay, they did this calculation based on 5. Right? So if you now do just a material balance, right, the amount of water in the system and the amount of salt in the system, then you're going to be able to solve, okay, and find that the amount of water that you need to make up, okay, due to the salt, due to wind losses, you're going to need to, instead of being 1.73%, Now I'm over 2%. And in fact, I'm going to need to make up 500 kilograms per hour. Now the next important calculation is pressure drop. Okay, so pressure drop, you're going to have some pipe losses, you're going to have some losses as it flows through the exchanger of a sort, and you've got control valves related to this, and then also you're going to have static head because this does have some elevation change. Okay, if you do this and then you also compute your pumping power, okay, you've got your delta P from up here, right? And then you need a volumetric flow rate. We have a mass flow rate, so just change that over to get it into volume. And an efficiency of 75% is a typical value. Then we see that we're going to require roughly 2.4 kilowatts of power to be able to pump this material through the circulating mechanical draft cooling tower. So we've got water loss and we've got pumping power. Now we're also going to have fans, right? Because it's a mechanical draft cooling tower. So the pumps are going to circulate the water. Now we need to blow air over our water. So for the fans, this information is from literature. But basically, there are some rules of thumb for how many square feet of surface per GPM, and therefore what your needs are going to be. So I have here my flow rate, just some conversion factors here. Okay, so this is the square feet per GPM, so I've got this into GPM square feet now, and then the 0.041 is how many horsepower per square foot. And again, this is a literature value. Converting this over to kilowatts, we get 1.61 kilowatts. So a lot of these are unit conversions, this and this. This is my horsepower conversion. This is my area per GPM. And so I end up with 1.6 kilowatts required for the fan. Okay? Now I'm going to, as I pump water, I always have to add chemicals in addition to just water. So we need the cost of materials for adding the makeup water. We're going to need cost of electricity for running our fan and our pump. Okay, the cost of the water. Okay, so we've got the chemicals to add to the water and the water. And so we end up with the total cost, okay, here just computing the electrical needs and the makeup water and chemicals for the makeup water of 35 cents per gigajoule. All right, so that concludes this example.